Alright, this is our first real-world example using our quadratics. Our situation is very simple. An object is thrown off a bridge. The height of the object can be found using this equation. And we're going to answer these questions. I'm going to draw a little picture so we can see what's actually happening here. So, here's my bridge. It's somewhere floating in the air. The rocket, an object is thrown, it goes up higher, and eventually it's going to land and hit the ground. Well, these have different places on my graph. For example, this is my starting point. This place where I release it, that is my y-intercept. That's this value here. I can already tell you that this is 128 feet in the air. Somewhere else in here I'll have the highest point. This right here, that point, that's the highest point it goes. And then this place right here where it crosses, it hits the ground, that's when I know my height is 0. It's hit the ground at that point. So we throw it off, it goes up a little bit in the air, and it falls to the ground. The one thing that is different about, or the big thing that's different between real world situations and math world, is if I was looking at this same equation or same function in math world, it would look like this. And there would be arrows, and that would go on forever and ever. In the real world, we have a starting point. Again, typically your y-intercept. This is where it starts, goes up, lands, and stops here. So again, in the real world, we have defined spaces. In math world, we have arrows. They go on forever and ever. Okay, so let's go ahead, take this in our calculator, go to y1, clear it off, and let's put this in our calculator. Luckily, we don't have to figure the equation out. It's given to us. We have negative 16x squared. This may be t, but we put x in the calculator. Plus 32x plus 128. And I want to look at the table. There's my table. What we have here, this t, that's our time. That's our x value. That's our time. At my starting point, after 0 seconds, it's 128 feet in the air. That's the starting point. You throw it at 0 seconds, it's still sitting in your hand 128 feet up on the bridge. We want to figure out how high it is after this many seconds. So I look down to 1. At 1 second after I throw it, it is 144 feet off the ground. 3 seconds. I look down to 3 seconds. 380. It is 80 feet off the ground. I'm going to go through and label some of these points. This 128, this happens at 0, 128. This is my maximum up here. We're going to use this in a second. Where's my maximum? This maximum would be my vertex. If I look here, 144 here, and then surrounding the 144, my two y values are the same. So that means this is my vertex. That's my maximum. My maximum here is, after 1 second, it is 144 feet off the ground. And then this point over here where it lands, it takes 4 seconds to hit the ground, and after 4 seconds I've hit the ground. Your real world situations with quadratic functions, they are going to typically start at the y-intercept, hit some sort of maximum or minimum, typically maximum, and then finish at the next y-intercept. Sorry, not y-intercept, x-intercept. So we're going to start where x is equal to 0 and end where y is equal to 0, typically. Alright, what was the highest the object gets? Well, the highest the object gets was its maximum point here. That was 144 feet in the air. How long did that take? Well, that took 1 second. It was 1 second after it was thrown. It was 144 feet in the air. What is the y-intercept of the equation? The y-intercept was 128, but more specifically, what does the y-intercept represent? That's how high it started when it was thrown. It was thrown, or started its path, at 128 feet above the ground. There's an example we typically do later on, that a rocket is launched from a platform that is so many feet high. That's what this is. Or you're in a tree or on top of a building throwing a rock off, kind of like this one. Domain and range for the situation. Let's first actually go down here and do the domain and range for the function. This function, my functional domain, always, my functional domain for any quadratic is always negative infinity to positive infinity. My range, since it opens down, my range is going to be negative infinity to k. K is that vertex value, and k is going to be inclusive. So I have negative infinity all the way up to k, which is my y value of my vertex, to 144. So that's 144. That is what my functional domain and range look like. We want now to compare that to domain and range for the situation. The domain and range for the situation, they're trapped. Math world goes on forever, continuously, forever, never stops, all real numbers, negative infinity, positive infinity. Real world, we're trapped. We start when it's thrown off the bridge, we end here. Boom, done. So we only want those values. My domain is my smallest x value to my largest x value. My domain simply covers from here to here. So let's see what that looks like. Okay. Domain for the situation. My domain for the situation is going to be my smallest value. I start at 0 seconds. Typically, you're going to start at 0 seconds in the real world. I'm going to end 4 seconds later when it hits the ground. Now let's look at my range. My range. I'm no longer starting at negative infinity. My lowest y value is down here. The lowest place this ever hits the ground. It hits the ground, so we're going to include that ground. What's the highest? The highest is not 128. That's where we started from. The highest is actually my maximum here, 144, my k value. And that too is inclusive. So how are they different? The domain is completely different. We have all real numbers compared to just 0 through 4. My range is actually very, very similar, but instead of going down, dropping to negative infinity, it stops at 0.